Hello, I'm Laura Lewis, so welcome to the class on atomic structure. So now I can see myself. It's going to like minus myself on the screen, so I'm not looking at myself. There's not much value in looking at that. Okay, so let's start out. So F5, so start. So yeah, atomic structure. So this is for GCSE chemistry. So it's for all the exam boards. So it doesn't matter if you're doing AQA, EdXL, or OCR. They will all ask about atomic structure. You may know some of it from Key Stage 3 as well. Okay, so let's go to the next slide. So learning aims. So it's number 1, an overview of the structure of the atom and the subatomic particles. Number 2, an understanding why atoms have equal numbers of protons and electrons. And number 3, an understanding of what isotopes are and calculating relative masses from isotopes. So sort of quite easy things first of all, and the last one's probably one of the hardest things you'll get to in chemistry. So once you see that, it doesn't really get any harder than that, so don't panic. So you probably think, what is an atom? Okay, so actually the idea from atoms actually came from ancient Greece, and people thought, okay, if we chop something down far enough, we keep chopping something up, okay, far enough, at one point we're going to get to the smallest thing we can't chop any further. And the word atomos, so atom and os at the end, means indivisible, so you can't divide up any further. So if we had a really powerful microscope, you have to an electron microscope actually, a very specialist microscope, to zoom all the way down, you would find that every substance is made of atoms. Okay, so atoms are the smallest constituent particle of anything. So we're made of atoms, trees made of atoms, cats and dogs made of atoms, inanimate object, laptops made of atoms. So everything's made of atoms. The sun, okay, there isn't anything that isn't like a substance that isn't made of atoms. Okay, so we know today that the atom, okay, is a small nucleus with protons and neutrons and electrons orbiting outside in what's known as shells. Okay, physics you might see them as orbits. Orbits and shells are the same thing, often called shells in chemistry. That's a useful definition. Those are three-dimensional atoms. Okay, so there's about 100 different types of atom, and on the next slide we'll talk about elements and things. But element is a substance that is only made up of one type of atom, and all the elements are featured on the periodic table. There's going to be a separate video on the periodic table. All the elements like carbon, nitrogen, helium, hydrogen, all the way down to uranium and beyond, some new elements, all only made up of one type of atom, and we can see visually here. So yeah, a substance is formed from one type of atom is called an element. Okay, so these elements, so iron's an element, yeah, hydrogen's an element. So two or more atoms are chemically joined is called a compound. Okay, so water is a compound because it's H2O, so it is hydrogen and oxygen. Carbon dioxide is a compound because it's carbon and oxygen. Sugar is another one, so you may know C6H12O6 from photosynthesis, carbon, hydrogen, oxygen. So these are all they're kind of similar, aren't they? But salt, so sodium chloride is also a compound. So lots of things are compounds. So if they're not on the periodic table and they're still chemically joined, they're a compound. Okay. Other things you come across every day, mixtures. Okay, so you put sugar in your tea, you form a mixture of sugar and water. So it doesn't form a chemical compound called, I don't know, sugar water. It's just sugar and water, and that's a mixture. So things like you put sand and salt together and mix it around, it doesn't form a new compound. It just forms a mixture. Okay. So a little bit more about how atoms were actually discovered, because the ancient Greeks had ideas, but there wasn't any formal experiments to go on. So this kind of started in the early 1800s. Okay, someone else started thinking about it. So John Dalton proposed that substances are made of tiny hard spheres. Kind of makes sense, doesn't it? I suppose you would made of something really small. So atoms, different elements had different masses. So yeah, they were onto the idea there. Okay, he was getting onto the idea that, because obviously some things are feel like the denser, like lead would feel denser than say hydrogen or helium balloon. Okay, so you're getting the idea. Then J.J. Thompson, you may have heard of him. He contributed a lot to science, J.J. Thompson. So, and at the end of the 1800s, so yeah, it took a while. Different people talk about. J.J. Thompson was investigating cathode rays. Okay, so a cathode ray, okay, is a beam of electrons. So all it is this used to be on old televisions. That's actually how the light in old televisions used to be produced. Was that the cathode, the negative terminal, the power source, actually emits electrons when the voltage is high enough. Yeah, these are quite dangerous devices if not used properly. Actually, what's called as boils off electrons. So it's called Fairmionic Emission. It's getting a little bit advanced for GCSE, but I'm just saying that's what it's called. So the electrons are boiled off what's known as the cathode. You may know that from electrolysis, the cathode being the negative terminal. So that's a bit of a link into, so same thing, a cathode is a negative terminal of a power supply. So you've got two plates here, these are separate to this. Okay, so you've got a positive and a negative plate. And so he sent out a cathode ray beam because people knew that if you put a screen, this is a screen here, in front of a cathode ray tube, okay, so there's cathode, and this is the cathode ray tube. So it's a evacuated tube, so it's a bit like the inside of an old television. You may not have ever seen one, but it's a vacuum, and electrons come out of here, okay. When you say positive here, that means that the rest of it's positive. And the electrons come off here, and they're deflected upwards. Okay, they're actually attracted upwards towards that, and also that this plate is positive to attract them. So they come off here, they're attracted here and accelerated. They're actually very fast accelerated. If you study A-level physics, you'll go into a little bit more about this. You've got a bit of a chemistry physics crossover here. So yeah, the electrons come out here and they're being deflected towards a positive plate. So if they're being attracted and deflected towards a positive plate, they're always being attracted to a positive. The cathode ray, as it was called, is actually negative. Okay, we found out that they're actually particles called electrons. It's not a ray. It still sort of sticks the name a little bit because that's what they called them originally. But they're actually, cathode rays are actually electrons because they're attracted to a positive plate, or anything positive they're attracted to. So that he proposed, this is, you could be asked this question, what is the plum pudding model? Okay, the J.J. Thompson, the plum pudding model. So he thought that atoms were a sphere of positive charge, most of it was positive, and the electrons were kind of embedded, sort of like in like this, embedded into the positive charge, like a plum pudding. And you may be thinking, what is a plum pudding? So this is plum pudding. It sort of makes me laugh when I see a big Christmas pudding on the slide. This is a plum pudding, so it's very similar to a Christmas pudding, okay, or a figgy pudding, as the song goes. It's Christmas time while you're watching this. So yeah, but what they were saying was, so the positive charge is kind of like the bready main part of the pudding, and the electrons are embedded into it like the raisins. Okay, so you could get asked what the plum pudding model is. It might help to think about a Christmas pudding, like the positive charge being like the bread. If you've ever made one, it's like kind of made of bread and sort of suet and fat and other things, and the electrons are all scattered through it and embedded in it. Okay, so that's three-dimensional again, embedded in it. We know that that's not the case now, though. So who found that out? Okay, so it didn't look like our model of the atom we saw on the first slide, did it? So Geiger and Marsden, Geiger of Geiger counter fame. Okay, so another double famous Geiger counter fame. So early 1900s, a little bit of time passed. So again, this is not that long ago, really. Some of my say just my great grandparents' time, I think. So in the early 1900s, Geiger and Marsden were investigating how atoms are affected by radioactive alpha particles. South particles, if you don't know, you should look at the ionizing radiation videos. They have a positive charge. Okay, so alpha particles are a helium nucleus, and they've got a positive charge. They fired the particles because they knew this is they knew that. Okay, so they fired them at a sheet of gold foil. So gold foil can be really, really thin. Okay, so gold foil, you might have seen your input on mirrors, on food, or sometimes people put them on their nails and things. Okay, but gold foil is very, very thin. Okay, that's why they fired it. It can actually be made so thin, gold foil, it's an atom thick. So that's why they used it. It can be hammered, so it's a thin, very, very thin, like a screen. It's like very, very thin. So they fired the alpha particle at the gold foil. They expected the alpha particle, would just go through if the plum pudding of the atom was correct. So they expected them just to go punch through because they're quite a lot bigger than the atoms that they thought. However, something very unexpected happened. So some of the alpha particles bounced back or were deflected by the atoms in the gold foil. Okay, so you see they're emitted there. Some went through, that's true, and some bounced back. So they proposed that most atoms were empty space with a tiny positively charged centre. This is what it's called, alpha particles to scatter. So let's explain that again. So they fired alpha particles at the gold foil. Some went straight through, some were deflected. Okay, remember that deflected thing. So if the alpha particles are positive, they're being deflected. They're not attracted, so they must be deflected by something else positive, or they're literally just bouncing back over here. They're hitting something and bouncing back. That's only very few of them. So most are going through or being deflected, and some are bouncing back. So they must be hitting something in there, but it's small. Okay, so this is lesser than doing it. So that actually provided evidence that there was mostly empty space in the atom, but there was evidence for a nucleus and a positive nucleus. So this was evidence against the plum pudding model. So this ties into physics as well. Okay, and then even a little bit later, 1914. So Bohr, Niels Bohr, you come across him, you study physics at higher levels, you come across him even more. Different atoms release light with different energies. So that means that if you heated them up, like in a lamp, you have a mercury lamp or a sodium lamp's like a street light. He said that they all glow different colours. Okay, and that means they've got different energies. So suggesting these differences must be due to the different distance of different electrons and electron shells. Okay, because different electron shells have different energies. So I don't need to know too much about this, but it's very interesting to where the shells came from. So different lamps, different element lamps emit different colours of light. So they also have different electrons, because when electrons are given energy by an electric charge, they jump up and they fall back down again when that charge is gone, and they release light. That's actually getting into how laser works, which could be a different video. We won't get into it too much, but they emit light at different energies, and according to the different electron arrangements that you have here, that they emit different colours of light. So you see a light in the street light is a sodium lamp, but it's got very characteristic yellow light because the arrangement of electrons in sodium. Okay, and different other lights because they've got different elements in them. Okay, so neutrons. Okay, again, this was actually quite a late discovery as well. So in the mid-1900s, scientists had a good idea something else was in the nucleus, as a massive element is higher than the number of protons. So James Chadwick fired alpha particles at beryllium atoms, and unknown radiation was produced. At approximately the same mass as a proton, no positive charge, so it wasn't deflected. So they finally had evidence for the neutron. So this bit, so the neutron does not have a positive charge, and so it would not be deflected by, it could be picked up by a Geiger counter, but it wouldn't be deflected. Okay, so that's good to know. I've actually seen an exam question where they asked who discovered the neutron, so I also included this. Not often talked about too much in books. James Chadwick, okay, discovered the neutron. I remember that. It's mostly you get questions about application of things like how would you know it's a proton or a neutron? Is because it wouldn't be deflected. Neutron would not be deflected by a magnetic field. Okay, that's because it had no charge. It's more like application, but I have seen the old multiple choice that they said about who discovered it. That's why I included it here. Okay, so it might be good if you later pause the video and you can copy this down and write down a few notes. I always think it's a good idea to write down these things as notes. So I'll let you pause that for later, but I'll carry on myself. I can change the slide. Okay, so each subatomic particle, this is really important. Okay, each subatomic particle has a relative mass, so how much of it is, and a relative charge, the electrical charge. These are all relative to the mass of a proton. Okay, so if we say, because it's very tiny, the actual mass of a proton, if we say it's 1, we can measure everything relative to that. It's a bit like saying, comparing the planets to the size of Earth. We say Earth is 1, and we just say how big. I say Neptune 4. Okay, it's 4 times as big. Jupiter 100 times as big. The Sun 1,000,000 times. Okay, that's how this kind of works. Is that we choose something to be our base, and we measure from that. So we've chosen the proton to be our base. So what 1? Okay, neutron, same mass, 1. Electron, much smaller. Sometimes known as being negligible. It means it's so small it doesn't really, you don't really use it in chemistry. Okay, it's not really used when you calculate anything, so we don't really have to worry about it too much. Negligible, but let's worry about its charge. Okay, proton +1 again, because it's got its charge of +1. Neutron 0. Remember about the magnetic fields there, the positive and negative. Electron, yeah, you have to remember this, the -1 electron charge. That's very important there. So this is a good table just to copy down, and you have to remember this one. I don't think it's too difficult, and it can be applied to different situations, like what is this particle? It's like being attracted to a positive plate. It must be an electron. It's anything that's got a negative charge. Okay, same thing here. If you'd like to copy it down, you can pause the video and do that, because this is recorded, so you can pause me at any time. Okay, so let's moving on to looking at the actual numbers on a periodic table, and there will be another video about a periodic table. We'll just look at the basics at the moment. Okay, so you've got the top number. Okay, that's the mass number. It's the number of protons and the neutrons. So it's protons added. It's the number of neutrons. I say the top number rather than the so I say the usually the top, but it can be on the bottom. Always the bigger number. Okay, if you remember, it's the protons added to neutrons. It has to be the bigger number. Okay, the bigger number. The atomic number, this is the one here, tells you the number of protons found in an atom. Ooh, I don't know what's happened there. Atom. The number of protons is different for each element. Okay, so an element, we move up, kind of formatting. There we go. So the element itself is actually known by its number of protons. So if, for example, sodium here, so that's sodium, Latin name natrum, that's what it's got, Na, but sodium, it's got 11 protons. If an atom doesn't have electron, if an atom does not have 11 protons, it is not sodium, it is something else. Okay, if it has 12, it's actually magnesium. So the protons is important to know what element it is. That's how you find it on a periodic table. Okay. So yeah, each element has a unique number of protons to it. Carbon 6, hydrogen just 1. Okay, so let's have a think about what this is telling us. So this is potassium. Okay, yeah, sorry. So this has got 90. This is atomic number 19 protons. 39 is the mass number, so something added to 19 must equal 39. So 19 plus 20 would give 39, and that would be 19 plus 20 would give 39. So it's got 20 neutrons. Okay, we'll do a bit more practice just soon. Let's just go back for a minute. So let's look at the atomic number for a minute there, and so this has got 11 protons. Remember, they're positive, so the overall atom is neutral. Okay, so if it's got 11 protons, it also has 11 electrons, because the protons are positive, so 11 plus, and 11 minuses would give 0. Okay, let's have a look at this. This is boron. Oh, so I can write on it. I'm just going to go zoom out for a moment. Let's go back to boron. Okay, protons, 5. Electrons, oh, we know that, 5. Neutrons, 5 plus something's 11, 6. Easy enough. Okay, carbon, protons, 6. Electrons, 6. Easy, isn't it? This time, 6 plus 6. Even easier. Nitrogen, same story. Protons, 7. Electrons, 7. Neutrons, 7. Wow, chemistry is very easy. Actually, say it was the hardest subject. Okay, protons for oxygen, 8. Electrons, 8. 8 plus something, 16. 8. A bit of a math lesson as well. Bonus. Protons, 9. Electrons, 9. Neutrons, oh, not 9 this time, 10. Okay. It doesn't really get any harder than this. Protons, 10. Electrons, 10. Neutrons, 10. So sometimes they've got the same number and sometimes they haven't. Okay, so this is a good thing. Let's go back to our presentation again. Ooh, all filled in this time. So it's good actually to go over this in your own time. So you've got the nucleus containing the protons and the neutrons. You've got the electrons, or they're individually labelled here, proton. This is representing a neutron. Okay, so it's got, this is a shell. Okay, so let's just fill that in again together. Set text box. This is a proton, positive. Okay. Neutron. Okay, this whole thing. I'm going to turn around, I might mute myself or something. I don't want to do that. Okay, this whole thing is a nucleus. Sorry if I went a bit silent. I think I might have accidentally muted myself. Only for a second, it should have been. Okay, this is a shell. It's got the electrons orbit in. And last one, the electron itself. Capital. It doesn't actually have to be a capital, but I'm going to follow as I continue as I've gone on. Okay, so it's a good thing to pause that. Okay. Right, you pause. Okay, I'll bring it up again so you can pause. Okay, it's a good idea to pause that and go through it on your own time. Okay, I'm going to move on. Just letting you have a look at that. I can actually move on to the next slide. So isotopes. Okay, so what are they? Often, I remember I used to look at the periodic table on the wall when I was at school, and it's 35.5. I used to think, how can something have a mass of 35? You can't get half a neutron, can't get half a proton. Why is that? So I finally answered it one day at GCSE. So this is what you'll see. So really, it's just an average. Okay, it's an average of isotopes. So chlorine exists in 2 forms on Earth called isotopes. They have the same number. They're the same number of protons, but different numbers of neutrons. So this is, they've both got 35. So it's got 35. Sorry, this one's got 37. They both have 17 protons, but chlorine 35. So how you say an isotope's name? You say its name and you say its mass after it. So chlorine 35 has 17 protons, but 18 neutrons. As chlorine 37 has 17 protons, 20 neutrons. Okay, so atomic mass 34.97. Relative abundance is how much there is on Earth. So 76% of chlorine on Earth is chlorine 35, and 24% on Earth is chlorine 37. Notice they're up to 100%. So we've got that on the next slide. So let's have a look. So calculating the relative mass of chlorine. So you multiply the mass number by the relative abundance. Okay, so 35 times 76 equals 2660. Okay, so you multiply the mass, okay, by the relative abundance. So just go for the whole numbers. 35 times 76 is 2660, and 37 times 24 is 888. Well, really, we're just working out an average here. It's very, very much like maths. Add your results together, okay, and divide this result by 100. So get them together, 3548. So 3548 divided by 100 is 35.48, or rounded to 35.5. So it's just an average, okay, of those isotopes abundances. So it's just the average. So the average, if you picked a chlorine atom out at random in the world, that it would be most likely to be chlorine 35, because it's kind of closer to that. But overall, the average is 35.5. So yeah, the individual chlorine atom would be a 35. It would be a 37. Okay, so let's just go over that a little bit again. So isotopes, so the same number of protons, because that's what makes it the element, different numbers of neutrons. Okay, so other isotopes. So you've got other isotopes there. So hydrogen. So hydrogen's special because it's got names for its isotopes. Hydrogen 1, also known as protium. Hydrogen 2, also known as deuterium. And hydrogen 3, tritium. Okay, carbon 12 and carbon 14. They haven't got their own names. It's called carbon 12 and carbon 14. So let's have a look at this. So hydrogen 1, protium. So how many protons? 1. Electrons, same number. Aha, neutrons. This is the one that makes people confused. 0. Hydrogen 1. Okay, protium has 0 neutrons. Deuterium. Protons still 1. Electrons 1. Neutrons 1. Okay, it's quite. Hydrogen 3. Tritium. These are quite rare things. Protons still 1. Electrons still 1. Neutrons, however, 2. Also known as heavy hydrogen, you may hear it called. Carbon 12 and carbon 14, very common ones to ask about. Protons, look at this, 6. Electrons, 6. Neutrons, 6. We saw that earlier. Carbon 14, you may hear it's carbon dating. Carbon 14 is using carbon dating. So protons, 6. Electrons, 6. Neutrons, 6 plus something called 8. Okay, so it's going to go quickly over what we have learned. So overview is structure of the atom, subatomic particles. There's probably in this video, there's quite a lot of times we want to pause it, isn't there? There's quite a lot of things going on. You probably want to pause it. So the structure of the atom, subatomic particles. Remember, we filled in here. Very, very important. Okay, the structure. Okay. Understanding why atoms have equal numbers of protons and electrons. So that's through the charge, isn't it? So remember, protons +1, electrons -1. That these two had to cancel out to make overall neutral charge of 0. And understanding what isotopes are. So they are atoms that have the same number of protons with different numbers of neutrons. Calculating relative masses. So the step-by-step process was here. Again, you are able to pause that. Step-by-step process of how to calculate the relative mass. Okay, using the abundance and the atomic mass. Okay, and usually round it just to one significant figure at the end. Okay, thank you for joining the class. I'm going to stop there. Hope to see you in another one. Goodbye.